Welcome. Today we are talking about the electric field. If we look at the space around an electric charge, it might seem empty, but it is actually filled with invisible forces. Watch how the space changes. A single isolated charge creates a simple web, but if we add another one of the opposite sign, we get a beautiful, complex pattern that we call a dipole. And what if they have the same sign? The field changes again. The lines repel each other, and in the center, a zone emerges where the forces completely disappear. A simple change in the arrangement immediately alters the entire geometry of space. We have all heard of Coulomb's law. It tells us how much force acts between two charges. But what if we remove the test charge from the equation? What remains in the space around the source? What remains is the electric field. Mathematically, we get the field when we divide the force by a small positive test charge. It is not a property of that test charge, but a property of the space itself. The electric field tells us in advance exactly how much force a small positive test charge would feel if we were to place it at any point in the space around the source. How do we know in which direction the field points? The rule is quite simple. The direction of the electric field is always the exact direction in which a small positive test charge would move. That is why the test charge runs away from a positive source, following the red arrows. But if the source becomes negative, the direction flips. The blue arrows now pull our test charge straight toward the source. We can represent the field using vectors. Notice how the vectors are not the same everywhere. Closer to the source, the arrows are long because the field is strongest there. As we move further away, the arrows become much shorter. The strength of the field decreases with the square of the distance. However, drawing thousands of arrows can look chaotic. That is why we connect local vectors into a global picture, into electric field lines. If you imagine a single line, the tangent at any point along it shows us the exact direction of the field. There are strict rules for these lines. First, they always start at a positive charge. Second, they always end at a negative charge. Third, the stronger the charge, say twice as strong, the more lines originate from it. And the most important rule of all, electric field lines never ever cross each other. Let's look at a clean textbook example. A single isolated positive charge in the center. Its field lines radiate outward in all directions. If we place our test charge there, the force pushes it away from the center. Now let's look at the negative charge. Do you notice the similarity? The general shape is identical. We still have that beautiful radial symmetry. The only difference is the direction. The lines now point inward, pulling our positive test charge toward the center. Things get really interesting when we introduce two charges into the space. Two equal positive charges repel each other. The lines in the middle bend and push away from one another, leaving a perfectly calm, neutral point in the center, where the total field is exactly zero. On the other hand, a positive and a negative charge make a perfect pair. They form an electric dipole. The lines flow smoothly from the positive to the negative side, creating one of the most important patterns in nature, the foundation of many molecules around us. And what happens when a dipole is placed in a strong external uniform field? That field doesn't just pull the dipole in a straight line, it creates a torque. It rotates the dipole until it is perfectly aligned with the external field lines. When the charges have different magnitudes, the picture shifts. The stronger charge dominates the space. Its extra lines do not find an end on the weaker charge. Instead, they travel off into infinity. How does nature calculate all these complicated shapes? It uses the principle of superposition. Imagine that each charge creates its own, completely independent field.
At any point in space, we simply take the vector of the first field and add it to the vector of the second field, using the head-to-tail method. The resulting vector is our actual total field, and this rule applies whether you have 2, 4, or a billion charges in your system. If you look closely at this complex picture, you will notice something else. Where the field lines are densely packed, the electric field is at its strongest. Our test charge feels the greatest push there. Where the lines spread apart, the field is weak. And remember, we are looking at this on a flat screen, but the field is a real three-dimensional structure in space. That is why we can draw not just lines, but concentric spheres around the source. These lines, or surfaces, are called equipotentials. They are the best partners to field lines. They always intersect at perfect right angles. If our test charge moves along this equipotential line, its potential energy doesn't change, and the work done by the electric force is exactly zero. Can we create a perfectly uniform field? Yes, we can. All we need to do is place two large flat plates parallel to each other, one positive and one negative. Between them, an idealized uniform field emerges. The lines are perfectly parallel and equally spaced. If an electron enters this field at a high speed, the force will constantly pull it toward the positive plate. Its path bends into an elegant parabola, just like a ball thrown in Earth's gravitational field. Now for an incredible property of metals. If an external uniform field encounters a conducting shell, something magical happens. The free electrons in the metal rearrange themselves, perfectly canceling out the external field inside the cavity. The lines bend around the metal, and inside the field is absolute zero. This is a Faraday cage, your ultimate protection against electricity. We can easily remove excess charge from a conductor like this. All we have to do is connect the conductor to the Earth. The excess electrons will flow down the wire, and the object's potential will level out to zero. Let's finish with a couple of beautiful geometries. Look at this charged ring. From every point on the ring, the field radiates toward the central axis. But because of its perfect circular symmetry, all the sideways forces cancel each other out. What remains is a single pure push along the axis of the ring. And exactly in the center, the field is zero. And here is the quadrupole, 4 charges arranged in a square. The picture looks incredibly complex, doesn't it? But if you look closely, you will see that even this intricate web perfectly follows those simple rules from the beginning. Everything starts at a positive charge, ends at a negative charge, and nothing ever crosses. And that is the essence. Every situation in the universe, no matter how complex, comes down to a few basic principles. Remember the definition of the field as force per unit charge. Remember how the lines travel from positive to negative. Do not forget the principle of superposition that adds it all together, and the equipotential lines that cross them at right angles. These tools allow you to read any charge configuration in the universe. Thank you for watching. If this video helped you better understand the electric field, please leave a like and subscribe to the channel so you don't miss our next physics animations. See you soon.